Hi everyone. So today is our 12th and last lecture of this TA session for NPTEL course Introduction to Algebraic Geometry and Commutative Algebra. Today's syllabus we will do problems from this syllabus, integral extension and Cohen-Seidenberg theorem. So let us go into the first problem that says that let A be an Noetherian integral domain and let P be a non-maximal prime ideal of A so that the localization AP cannot be integral over A. Now we prove the claim by contradiction. Assume that AP is integral over A and consider the canonical localization map from A to AP by A going to A by 1 and so now since AP is assumed to be integral over A, the lying over theorem applies that says that the induced map on spectra I upper star from spec AP to spec A is surjective. Now recall the description of the prime ideals of localization. A prime ideal of AP corresponds exactly to a prime ideal Q of A such that Q intersection A minus P is phi, which is equivalent to Q contained in P. Hence the image of I upper star is precisely image of I upper star equals to Vp equals to all the prime ideals Q from spec A such that Q is contained in P. Since I upper star is surjective, by the integrability assumption we obtain spec of A equals to V of P, and in particular every prime ideal of A is contained in P. But every maximal ideal of A is a prime ideal, so every maximal ideal must be contained in P. This forces P itself to be maximal. Now, if M is maximal ideal of A, then M is contained in P, and since P is prime, it must contain some maximal ideal. And the only possibility is P equals to M. Thus P is maximal. This contradicts the hypothesis that P is non-maximal, therefore our assumption was false and AP is not integral over A. Now let us move on to the next problem, which says that let A be an integral extension, let A dash be an integral extension of rings of A and let P is a prime ideal of A. Suppose that there is only one prime ideal P prime from spec A prime lying over P, and we have to show that P prime A dash P dash is the only maximal ideal of A prime P prime, that is A prime P prime is local, and B, the canonical map AP to A prime P prime is a local homomorphism, and equivalently P dash A dash P dash and intersection A suffix P is P of A suffix P, and for C A dash P dash is integral over A dash A suffix P. Now shall try this for 10 minutes, then we shall start discussing this. Okay, so let us start solving this. Let us denote S equals to A minus P and S prime as A prime minus P prime. Then AP equals to S inverse A and A prime P prime equals to S prime inverse A inverse. Now in step 1 let us prove the localization preserves integrality. Since A prime is integral over A, every element of A prime satisfies a monic polynomial with coefficients in A. After localizing, the same monic equation shows that every function in A prime P prime is integral over A suffix P. Hence, A prime suffix P prime is integral over A suffix P. This proves our part C, which says that A prime suffix P prime is integral over AP. Now, the ring AP is local. Because AP is integral over itself, the localization AP has prime ideals corresponding exactly to prime ideals of A contained in P. In particular, its unique maximal ideal is P A suffix P. I mean, if M is a maximal ideal of A suffix P, then M intersection A is a prime ideal contained in P, hence a prime of A lying under P. Now, in proof of A, let M prime is a maximal ideal of A prime suffix P prime. We show that M prime equals to P prime into A prime suffix P prime. Set M equals to M prime suffix AP. Since A prime P prime is integral, suffix P prime is integral over AP, by step 1 the residue ring A prime suffix P prime by M prime is a field integral over the subring AP mod M, and A integral domain over a field is itself a field, hence A suffix P mod M is a field. Therefore, M is a maximal ideal of A suffix P. But A suffix P has only one maximal ideal, namely P of A suffix P. Thus, M equals to P of A suffix P. Now, let Q prime be a prime ideal in A prime corresponding to M prime under localization. So, M prime equals to Q prime into A prime suffix P prime, and Q prime intersection S prime is phi, that is empty. Since M intersection A is P, the ideal Q prime satisfies Q prime intersection A equals to P, and by hypothesis there is one prime of A prime lying over P, namely P prime. Hence, Q prime equals to P prime, and consequently we have M prime equals to P prime A prime suffix P prime. So, P prime A prime suffix P prime is the unique maximal ideal of A prime P prime, and A prime P prime is local, and this proves our A. Now in step 4 we prove B. The canonical map from AP to A suffix P mod A prime suffix P prime sends the unique maximal ideal P of AP into the maximal ideal P prime into A prime suffix P prime. Equivalently, its contraction of the maximal ideal of A prime suffix P prime is the maximal ideal of A suffix P, and P prime into A prime suffix P prime intersection AP equals to P of A suffix P. Thus, the localization map is local, and this proves B. Therefore, we have shown that A prime suffix P prime is local with maximal ideal P prime into A prime suffix P prime. The natural map A suffix P to A prime suffix P prime is local, and A prime suffix P prime is integral over A suffix P. Therefore, we are done. Now, let us prove the next question, and which will be our last, but we will do it one by one. So, let us try to understand the problem first, then we will start solving this. Okay, so let us start solving this problem. Let B an A algebra. Let B be an A algebra over a ring A, and let G uh, uh, be a sub finite group of automorphism of all A algebras. Oh, automorphism of B as A algebras be a finite group of A algebra automorphism of B, and the subset B prefix G as x of B such that sigma x equals to x for all sigma of G is called the ring of invariance of G, so that every x of B is integral over Bg, and in particular B is integral over B prefix G, and therefore dimension of B prefix G is dimension of B. And if B is an A algebra of finite type, then there exists an A sub algebra A prime of B prefix G of finite type over A such that B is integral over A prime. If A is Noetherian and B is an A algebra of finite type, then B prefix G is also an A algebra of finite type. In particular, B prefix G is Noetherian. Now, let S of B be a multiplicative closed subset such that sigma of S is a subset of S for every sigma of G, and let S prefix G equals to S intersection B prefix G. Then the action of G on B extends to an action of S inverse B, and S prefix G inverse of Bg is isomorphic to S inverse B prefix G. Now we prove the for answer 3 we prove the 4 parts in turn. For A, every element of B is integral over B prefix G, and let x belongs to B. Consider the polynomial Px of t equals to product of t minus sigma x running over sigma of G. And now since the set sigma of x, where sigma belongs to G, is permuted by the action of G, the coefficients of Pxt are fixed by every tau of G. Hence, Pxt belongs to B prefix G of t, and moreover, P suffix x of x equals to 0. Thus, x satisfies a monic polynomial with coefficients in B prefix G. So, x is integral over B prefix G. Since every element of B is integral over B prefix G, the extension B mod B prefix G is integral, and for integral extensions, the induced map on spectra is surjective and preserves the cool dimension. Therefore, dimension of B prefix G equals to dimension of B. Now, construction of a finite type subalgebra. A prefix is a subset of B prefix G. Assume that B is of finite type over A, and choose generator B equals to A of B1 up to Bn for each I from the monic polynomial Pi of t equals to product of t minus sigma of Bi, which belongs to B prefix G of t. Now let A prefix is a B sub algebra of B prefix G generated by all the coefficients, all the polynomials P1 up to Pn. Then A prefix is of finite type over A because only finitely many coefficients are adjoint. Since Pit lies in A prime t, and since Pi Bi equals to 0, is Bi is integral over A prime. Because B equals to A of B1 up to Bn, which is a subset of the integral closure of A prime in B, it follows that B is integral over A prime. Thus, we have produced a finite type A subalgebra A prime subset of B prefix G such that B is integral over A prime. Now, try to understand this C part, and then we will start discussing after 10 minutes. Okay, so now let us prove the C finite type of invariant ring. Assume now that A is Noetherian and B is finite type A algebra. By part B, there exists a finite type A algebra A prime of B is prefix G such that B is integral over A prime. Since B is also of finite type over A and A is a subset of A prime and A prime is a subset of B, the ring B is a finite type A prime algebra. An integral algebra of finite type over a ring is finite module. Hence B is a finite A prime module. Because A is Noetherian and A prime is a finite type A algebra, the ring A prime is Noetherian. Therefore, every submodule of the finite A prime module B is finitely generated, and in particular, the A prime submodule B prefix G of B is finitely generated. But B prefix G is an A prime module algebra, and being finitely generated as an A prime module implies that it is a finite type A prime algebra. Since A prime is finite type over A, transitivity of finite generation shows that B prefix G is finite type over A. And finally, since A is Noetherian and B prefix G is finite type A algebra, B prefix G is Noetherian. Now we prove the fourth contingent, but again read it for 5 minutes. Okay, let us prove the section 4, localization and invariance. Assume that S of B is a multiplicity closed and G stable set, meaning that sigma of X is a subset of S for every sigma of G. Set S to the power G as S is intersection B to the power G. Now for step 1, the action of G extends to S inverse B. For sigma of G, define sigma of B mod B by S equals to sigma of B by sigma of S, where B belongs to capital B and small s belongs to capital S. This is well defined because B by S equals to B prime by S prime. Then there exists U of S such that U of S B prime minus S prime B equals to 0. And applying sigma and using sigma U belongs to S, we obtain that sigma of U into sigma of S into sigma of B prime minus sigma of S prime into sigma of B equals to 0. So sigma of B mod sigma of S equals to sigma of B prime by sigma of S prime in S inverse B. Thus G acts on S inverse B. Now step 2, every element of S becomes invertible already after localizing at S to the power G, and fix small s of capital S. Consider the polynomial PST equals to product of t minus sigma s, where sigma belongs to capital G. Its constant term is minus 1 to the power mod G into product of sigma s, where sigma from G, which lies in Sg, uh, because S is multiplicatively closed and G stable. Now in localization S prefix G inverse B, the constant term of PS becomes invertible since PS of S equals to 0 and PS is monic. The standard integrality lemma shows that S is invertible in S prefix G inverse B. Hence every element of S is already invertible in Sg inverse of B. So by the universal property of the localization, there is a canonical isomorphism S inverse B isomorphic to Sg inverse B. And step 3 says that invariance commutes with localization at S prefix G. Since S prefix G is a subset of B prefix G, localization at S prefix G is defined on B prefix G. Moreover, localization is exact and commutes with finite products. Using B prefix G equals to kernel of B to product of B to sigma of G, we obtain sigma prefix G inverse B prefix G equals to kernel of S prefix G inverse B into product of Sg inverse B, and the right hand side precisely is Sb inverse B of G. Since S inverse B is isomorphic to S inverse B, we conclude that Sg inverse B to prefix G is isomorphic to S inverse B prefix G. This proves our D. So I hope you like this course throughout, and we'll meet our next semester, and this ends our course here. Thank you.